Hello everyone, I'm Lixiao Zhao from Southeast University. Today, I would like to talk about using viscosity modifying a mixture to reduce diffusion in cement-based materials, effect of molecular mass. The main topics include 8 parts. The ingress of deleterious ions, such as chloride, in reinforced concrete structures is essential to determine the service life. At present, measures to mitigate the ingress of external ions in concrete mainly include reducing water-cement ratio, increasing the quantity of binders, and adding supplementary cementitious materials, most of which aim to densify the binder matrix in concrete. However, these measures have also brought secondary problems, such as increasing the weight of the structure, making the matrix cracking easier. So, we want to improve the ability of concrete to resist the corrosion of chloride on the basis of not increasing the compactness. Stokes-Einstein equation indicates that the higher the viscosity of the solution is, the greater the resistance to particle movement is. But what happens when the scale is narrowed to the ionic level? The association and entanglement between adjacent polymer chains of VMA lead to the formation of three-dimensional network and the hydrogen bonds in solution, which gives the solution a high viscosity. Let's take an example. A fishing net is equivalent to a three-dimensional structure formed by the entanglement of polymers, and the fish inside is equivalent to particles that need to pass through the polymer solution. When the fish is big enough, what it feels is the resistance given to it by the entire net, which is bulk viscosity. When the fish is relatively small, what it feels is the resistance given to it by a single mesh, which is microviscosity. Microviscosity is usually smaller than the bulk viscosity and reflects the viscosity behavior of a medium on a smaller length scale. The size of chloride ions is much smaller than that of polymer, so microviscosity is the key to affect ion diffusion. VMAs with small molecular mass have lower efficiency in increasing viscosity. However, when the molecular mass becomes too large, VMAs can no longer increase the microviscosity or even decrease it, while the bulk viscosity remains unchanged. Because the pores of entanglement between adjacent polymer chains of VMA will become large, providing free paths for ions to go through, just like they go through water. Although the solution has a remarkably high viscosity in such cases, therefore, determining the suitable molecular mass range is essential for mitigating chloride diffusion. The experimental program is divided into 5 parts, corresponding to 5 explorations, including solution conductivity test, isothermal calorimetry test, mortar mechanical property test, chloride concentration profile test, and MIP. The solution microviscosity is often assessed through the values of solution conductivity, so we use the polyethylene glycol, also can call it PEG, with different molecular mass as the VMA to characterize the diffusion behavior of chloride on the different given bulk viscosity by conductivity test, showing that the bulk viscosity of solution increases exponentially with the addition of PEG regardless of its molecular mass, and the conductivity of solution containing PEGs decreases with the bulk viscosity. It is also noticed that PEG with lower molecular mass exhibits higher efficiency in reducing the conductivity at given bulk viscosity. This phenomenon emphasizes the significance of molecular mass for reducing ion diffusion in solution. Through the further analysis of the previous two figures, we found that the slope of the part covered by the green shading is much smaller than that of the red shading, demonstrating a decline in efficiency in reducing the conductivity. Therefore, the turning point molecular mass 400 is regarded as the lower limit. Based on this equation, we acquire the relationship between the decrease of unit mass VMA solution conductivity and the molecular mass under given viscosity, found that the increased capacity of microviscosity for per unit mass VMAs doesn't increase with the increase of molecular mass when the molecular mass is greater than 1500. So, the molecular mass 1500 is regarded as the ceiling. And isothermal calorimetry test indicates that the smaller the molecular mass of the PEG is, the more obvious the hydration retardation effect is. The reason is that PEG has a double amount of hydroxyl of the amount of its own. PEG with smaller molecular mass has more molecules at the same mass, and correspondingly more hydroxyl groups. Hydroxyl easily forms hydrogen bonds with oxygen ions on the surface of anhydrous compounds, so PEG can be adsorbed on the surface of cement to retard cement hydration. Meanwhile, the PEG added for the purpose of inhibiting ion transport will inevitably inhibit the diffusion of cement hydration products, forming a high concentration range of hydrogens around cement particles and retarding hydration. For mechanical property, the compressive and flexural strengths of mortar are lowered with the increase of molecular mass and content of VMAs, and the presence of PEG, increasing the total property of mortar and coarsening the pore structure by increasing the volume fraction of pores between 100 to 1000 nanometers. Adding PEG can reduce the chloride diffusion coefficient of mortar, but not obvious at 7 days. After 28 days of exposure, the samples containing 5% of PEG with a molecular mass of 1000 exhibits the minimum diffusion coefficient, which is 30% lower than that of the control group. For this unusual phenomenon, we believe that the effects of PEGs include increasing the viscosity of pore solution, retarding cement hydration, reducing the chloride bonding, and introducing or entrapping of bubbles. At 7 days of exposure, the second and third effects dominate the diffusion of the samples with the presence of PEGs, and at 28 days of exposure, the first effect dominates the diffusion, due to the chloride bonding achieves equilibrium. The conclusions have been presented, so I will not repeat them. I just want to emphasize the last point of conclusions. The steric hindrance, also can call it steric obstruction, which is mainly dependent on the molecular mass of the organic solute rather than its structure, directly determines the microviscosity of a solution. That is the end of my report. Thanks for your attention.